Hey, and welcome to our sixth video tutorial, and today we're going to be talking about box fitting. So what is box fitting? Well, basically what we want to try to do is fit our members into the box in such a way that we maximize a particular dimension. Now, the most common instance of this that you might think of is diagonal box fitting. That is, if we have, say, maybe a girder part that's only maybe got like a top chord and then it has some webbing that comes down. I think 2 years ago, 2013, basically our top and bottom members of the bridge were all diagonal box fits. So let's give an example of that. I'll kind of take a look at a bridge here. So basically, for now, I've just kind of neglected looking at the vehicle passageway rules from 2014. I'm just kind of taking a look at what, a typical stacked bridge, and hopefully you recall the definition of a stacked bridge from a couple lessons ago. But basically, what I have here is a top chord that goes across and a bottom chord that goes across as well. And they're all connected together with bolts, as you can see, and then we have webbings that go through like this. Now you can see the webbings are connected, and actually I'm borrowing that connection that we designed from the previous lesson. So I'm using that information, my guess at what our connections will be, to inform how we go about optimizing the dimensions of the bridge. So as soon as you have one thing that you've already built off, you can use that in order to inform how you proceed in the design with certain dimensional optimizations. So keep coming up with connection ideas and all that, and it'll help to basically come up with better ideas of how you can optimize these things. So let's take a look at what this looks like in cross section. You can see I already have my boxes stacked on top of each other in the elevation view. In the section view, here you can see I've pretty much rotated the boxes to fully optimize the dimension for the depth of the bridge, overall depth from center line to center line. You can see here it's approximately 11 inches and 13/16. So zooming in here, you can see, wow, okay, I've really pushed the limits. These are pretty much perfectly touching both edges. Oh dear, zoomed in too much. Both edges on these, and also for the female part. Oh wow. So I am absolutely pushing this to its limit, but that's a good thing, and I'll explain why a little bit later. So I've put the male part on the bottom, you can see, and these are all pretty much fitting in the box as tight as you could possibly get them. Now the question is, how does one figure out what that angle should be? How do you know what's the best angle to orient your box in? Since if you were to start, let's say, with a box like this one, and then draw a diagonal, that diagonal technically doesn't adequately represent the width of this top part here and the width of the base here. As you can see, if I drew a center line to center line along this member here, it doesn't align perfectly with the corners of the box. Now, that might be a little cause for discomfort. You might start to think, okay, well, how do I figure out what that angle should be? I pondered this actually quite a bit when I first encountered this issue. Now, there is actually a mathematical solution to this problem, but it's not a simple one. I derived the solution, but unfortunately it's actually an implicit equation in terms of the angle that you would rotate the box. So how do we go about solving implicit equations? Well, of course, we rely on computers. So we're going to find an iterative solution using this trusty little spreadsheet that I've kind of come up with. So pretty much, you don't see it here, but I'm actually performing a bunch of iterations, roughly 20 iterations, in order to get convergence to a particular value. Now, you don't need to know how the actual equations and everything work in order to be able to use it, but I just thought it was kind of interesting to show that. Now, I've reduced it down to something as simple as essentially just inputting what the dimensions of your box are. In this case, I'm inputting the dimensions for my 6-inch by 4-inch box here, and as my input variables, I have S, in this case, for a square tube that you're placing as your top number. As in this case, I'm using a square tube for my top chord. And then I have some kind of characteristic width at the base. And if you remember from the previous lesson, for my female part, this distance from here to here should be roughly 1/2 inch. So I can just go ahead and put in those values. So my side length on the top number is roughly 1 inch, and at the base it's 1/2 inch. So S equals 1 inch, and W equals 1/2 inch. And there you go. You have basically your determined theta value. That's this angle here. You just have some kind of vector program to draw it out so you can kind of see it better. But basically, you have the angle here, and then you also have a length from the top of the box to the bottom there. So that's our characteristic L. So I can just take that, plug it in. Oops. Oh dear. There we go. And look at that. So now if I actually measured from the top of this to the bottom there, it would actually be 6.54 inches. And the angle that the box is rotated at is actually 30.866. So you can directly use those values in order to do it, and you can see how perfect the result is. And I have a similar program on the next tab for circular tubing. And in this case, remember the circular tube is 1 inch in diameter, and this dimension should be 1/4 inch. So similarly, I'll type in 1 inch for the diameter of the top tube, or rather bottom tube in this case, and W equals 0.25 or 1/4 inch. So there you have it. Calculates it for this as well. And you can see actually this is a slightly different angle, and it's a different formula as well. Oh my. I think my computer is bugging out. But what does that mean overall? Why not just, who cares really about, these dimensions anyways? Why don't we do something like this, where we're just really simply stacking the boxes like this? You don't have to go through all the fuss of using that crazy spreadsheet, and just kind of do this. Why isn't this acceptable? Well, there are a number of reasons. Well, here you can see I'm verging on almost 12 inches depth here, where this is pretty much like 1 inch less. So you're losing about 1 inch of depth. And why is that significant? Well, let's take a look. So the deflection cost is roughly $1 million times the total deflection of the bridge. Now I've done a very simple example where I've idealized the bridge as a beam. I've applied a point load, the load value of P, and I'm measuring the deflection value delta. So delta, or the deflection, should be equal to P divided by K, where K is the lateral stiffness of my beam bridge. So if K can be computed as 48 EI over L cubed, where L is the length of the bridge, E is the Young's modulus, I is the moment of inertia of the idealized beam, that is the bridge, then I can take a look closer at I, the moment of inertia, and simplify a very simple equation as just A, the cross-section of each respective tube on the top and bottom, which should be fairly comparable to one another, times D squared, where D is the distance between the centroids of those top and bottom chords. So D squared is basically what we want to look at. And if D, in the case of our optimized dimension, is 11 inches and 13/16, this squared compared to this squared will be significantly more efficient. And in fact, I did a small hand calculation and figured out that the deeper version, this one, is actually 22.8% more efficient than this one. So you basically save 22.8% of your total deflection cost by just optimizing with that dimension alone. So that is huge. It might not seem like a lot, but that is absolutely massive when you're trying to save cost, especially with regard to efficiency. So hopefully that will encourage you to pursue some of these box fitting techniques. I'll upload this box fit calculator up into the Dropbox, And hopefully, if you find occasion to use it, then you'll know how to go about optimizing your box fits. So, hopefully that was useful. Until next time, I will wish you the best. All right, good night.